So thanks for the organizers' invitation. So today, my topic is computational pharmaceuticals, from molecular modeling to artificial intelligence and big data. I come from University of Macau. So first, I introduce a little the background of the research. As we know, the drug development process can be divided into two parts. The first is drug discovery, and we need to design the new molecules and get the good efficiency. And currently, they have a lot of computer tools to help us to design the new molecules. For example, the bioinformatics, and help us to find the new target, and the computer-aided drug design and help us for the new molecule designs. The second step is the formulation or the dosage form development. Once we get the new compounds, the patient cannot take the new compounds directly. We need to make it to the proper dosage form or formulations. Currently, the formulation development strongly rely on the personal experience by trial and error in the laboratory. And so this area, it is have no available tools, computer tools for us. So my idea is, can we develop the computer tools to help us to design the new formulations and the final product? So once we want to use the computer tools to design the new formulations, of course, obviously, we can go back to the drug design areas. So for the drug design, actually, this area can look back to the 100 years ago. In 1902, the Nobel Prize winner, the Fisher, already brought forward to the lock and key theory. In this theory, to think about the drug, the target is a lock, and the compound is the key, and the key can open the lock. So this one is a very simple one-to-one model, right? And in 2013, three chemists, Karplus, Levitt, and Washer, win the Nobel Prize in chemistry. And because due to the contribution of the multiple scale modeling for the complex chemical systems. And the Nobel Prize committee, they said that today the computer is just as important a tool for chemists as a test tube. Modern pharmaceuticals. Actually, the modern pharmaceuticals just started from 1950s, and the first generation pharmaceuticals, we can call it the industry pharmacy or physical pharmacies. And after 30 years of development, we achieved a great success in the industry pharmacy and the physical pharmacy. And from 1980s, the nanomedicines and the gene delivery, it is what attracted a lot of attention for the pharmaceutical scientists. However, the second generation nanomedicine, this kind of delivery system didn't achieve great success in the clinicals and real applications. The reason is complicated, and you can see the papers we published in Drug Discovery Today last year and get more details. And after 30 years, now we ask the next question. The question is, what's the next? And as we know, with the development of the computer power and the software and algorithms, today the computer is getting more and more powerful, and we have lots of them. So for the formulation development, usually we can divide it into these four parts. First is pre-formulation studies, and the second is formulation studies, and then we need to, for the manufacture, the process is also important. And finally, we need to test the products in vivo, and such as animals or the human bodies. Currently, we have over 1,500 drug molecules by the FDA approved in the recent 100 years. We have about 1,000 very commonly widely used the excipients, and about 150 different dosage forms, and finally we have a total over 30,000 the products available by approved by the FDA. So from this process we can see the formulation development, it is a multiple scale multidisciplinary subject. It combines chemistry, material engineering, and clinicals. And currently we have to do the trial and error by the personal experience of pharmaceutical scientists. And so the process is time consuming and high cost. So since it is so much complicated process, the question is impossible to predict the pharmaceutical formulations. And because this is much complicated than the drug design one-to-one models. And if it is the one tool doesn't work, can we use multiple tools to solve these questions? And so we can use for the pre-formulation study, we can use the quantum mechanics to predict the physical-chemical properties of the compounds. And also we can use molecular modeling to predict the formulation, the drug-excipient interaction. For the manufacture process, we can use process simulations. And for the in vivo behaviors, we can use biopharmaceutical modeling to predict the drug behaviors in the bodies. And in total, we can use data-driven artificial intelligence and put all this information together. So the computational pharmaceutical can integrate the molecular modeling, artificial intelligence, and big data to the drug delivery for better medicines. So it has several advantages. The first, it can change the trial and error to the data-driven, the AI systems. And so we can put all the personal experience and data together for the self-evolution, the AI systems. And also we can not only investigate the microscopic properties and both the molecular level mechanisms of the formulations. So next, I will use one example to show what it is, how to use in our formulation development. Solid dispersion is, as we know, is widely very popular the drug delivery systems or techniques in formulation development can be used to improve the solubility and the dissolution rate of the poor soluble drugs. We can use different euphilic polymers to solubilize the drugs. And the preparation method also very simple. We can put the powder of the drug and the polymers put it together, melting it, and then quickly cool down, get the amorphous state of the solid dispersion. However, currently we have 4 key issues still to be solved. The first is the solid state structure of the solid dispersion. The solid dispersion, how this technique has been invented in 1960s. After 50 years development, we still don't know how the drug and the polymers interaction and the solid state. The second question is, we know it can solubilize the drug and improve the dissolution rate, but we don't know how it works. And the third question is the aging issues. That means the physical stability of solid dispersion is quite poor. The drug easily to recrystallize in the storage period, and then formulation fail, and this very serious issues. And the fourth one, it is the in vitro and in vivo correlationship. And if we get the good behaviors or performance in vitro of the formulation, but we still don't know whether it works in the in vivo in the human bodies. So in our research, we use a simulated annealing method to simulate how the drug and excipient interactions of the solid dispersion. The temperature change is the same as the experiment. We rise the temperature above the melting point of the substance, and after it completes the melt, and then we quickly cool down to the room temperature and get the amorphous state of solid dispersions. And this is the results of our simulation. In the left side is a conventional theory of the amount of solid dispersion. In this theory, they think about the drug molecule just like a fish trapped within the network of the polymers. However, if we do the experiment of solid dispersion, then we know the drug is easily shifted out and recrystallize. However, if we can look back of the model of the traditional theory, the drug molecule, once the drug molecule trapped within the network of the polymers, it will be difficult to shift out. So this model, traditional theory or model, it have a different from the experiment. So we did simulation. We use the ibuprofen small crystals, you see this one, and polyethylene glycol as a model polymers. And the temperature change just like the same as the experiment. And we can see this is the simulation process. In the simulation process, the linear polymers started to bend and aggregate together to form a random coils. The crystal of the drug crystal will be broken, and the drug molecule will stick at the surface of the random coils. And this model always is different from the traditional models. And it can help us to explain first the drug molecule, the crystal was broken, and then the drug molecule dissolution rate will be improved. And the second it is, since the drug just stick at the surface of the random coils, and so it will easily shift out and recrystallize. So this explains the drug molecule and why it is the poor physical stability. And also we test different the polymers such as polyethylene glycol, polysamol, and PVP, and other polymers. We get the same results and also the different ratio. And also next, in the second step, we want to investigate how the drug dissolved in the water in the dissolution process. Then we added a very large water box to simulate how it is the drug dissolved in the dissolution. So from this one, we can see the drug molecule will quickly leave this the solid swing process. The polymer chain will start to become loose, and also it will be released in the solution, and finally the solid dispersion completely dissolved in the water. So this very clear the image how it is a dissolution process of solid dispersions. And also we investigate different the polymer solution process, and we compared the PEG, PVP, and polysamol, these three polymers. And from this figure, we can see in the dissolution process, the PEG and the PVP, the drug molecule is easily to aggregate together. That means it may form the precipitate in the dissolution process. However, the polysamol base, the solid dispersion, it can very good distribute in the solutions. And this, the reason, possible reason is polysamol. It is a kind of a surfactant that can prevent the aggregate of the drug molecules in the dissolution process. So this research can help us to design better formulations, right, to select the proper polymers. And the third steps we want to, if we use a binary system, just a drug and a polymer, it may not get the good performance of the dissolution. If we add another one, excipients in, for example, the surfactant, it can very good help us to dissolve to get the good formulations. So in this formulation, we add the SDS in the dissolution process, so we can see what it is behaviors of the Tanner resistance. So the Tanner resistance, we can see the surfactant and very good to solubilize or help the dissolution process of the drug in the solid dispersion systems. And also we compare the Tanner resistance and the binary resistance together. The right side is the experimental data, we can see, and so we can see the Tanner resistance containing SDS and Twin 80 is much better than the binary systems. And the left side is the modeling results. So we can see also the binary systems have a longest the very long dissolution rate, and however the SDS binary, the ternary system is better than the twin-based ternary system, and also better than the binary system. The possible reason is SDS is a negative charge the surfactant and then help the water penetrate into the solid dispersions. And 280 is a non-ionic surfactant. And here we use one case to show how our modeling help us to design the formulations. The model drug we use is lutein. Lutein is a very good molecule for our eyes. It is for the age-related macular degeneration. However, this lutein molecule is very, very water insoluble. And also, this one, if you take this compound and you cannot absorbed by the human body because it's not dissolved in the GI tract. So how to solubilize the compounds is very important. So in our experiment, first we did the user suggestion to solubilize the compounds, and we did the phase solubility diagram and found it can increase a little bit of the solubility of the compounds, but not a lot, and we cannot find a reason why. And then we did the modeling results to see how it is the compounds, the saturation work. So we use this is the beta saturation and the lutein molecules. So this in this simulation, and also we have a water box. We just delete the water for the clarity of the video, and also we can see the compound is just the stick at the surface of the saturations, and still have a majority part of the lutein. It is still in the water. It's a hydrophobic part. So that's why the saturation can not good solubility improvement of the luteins. Since we know the reasons, and then we know just the saturation alone it cannot get the good effect, so we add the other excipients, for example the plasma and the surfactant 280s, and to screen the formulation, and finally we get a good formulation. It is gamma saturation based formulations, and we get the over 500 solubility improvement than the original the pure drugs. And this is the simulation. We can see it can form is just like a micelle based the structures, and also dissolution rate is have significantly improved. And this is the DSC and FTIR and XRD results. So since the time limit, I will not talk too much details. And also we tested the formulation in the COX-2 cell uptake, and also we can see the new formulation get a significant improvement of the cell uptake than the original drug. And also we did the animal, the viability studies, the rats, and so we can see we get the over 6 times than the original APIs, and the improvement of the viabilities. It's much better. And also we already applied the patent and get published the research. You can, if you want to get more details, you can just read the papers. And also in the past 8 years, our group did lots of tried a lot of different formulations, how to use the modeling in the formulation development, and you can see some more details from the papers. And next part I want to share with us is artificial intelligence. How is this formulation on AI systems used in the formulation development? And AlphaGo, as we know, this very hot areas. This AlphaGo, these games can attract a lot of attention in 2016, and if you want more details, you can read the two Nature papers have been published in 2016 and 2017, and get the details of the AlphaGos. And here, however, the AI systems have been used in formulation development since the early of the 1990s. And here we summarize several of the examples how it is the AI system used formulation development, how the current formulation, the AI system in formulation development, it uses a very simple expert systems, or it uses simple the algorithms. Actually, it is just for the formulation optimizations. It is not very good for the formulation predictions. So in our research, we want to develop the very good the formulation prediction models for the future formulation development. Here we use 3 different formulation datasets to test our models, and the oral fast disintegration tablet, and oral sustained release metric tablet, and solid dispersions. All data come from Web of Science, and the formulation data includes the drug molecule and excipients, and also the ratios, and also the process parameters and the in vitro performance. For example, for the oral fast disintegration tablet, we use a disintegration time, and for the oral sustained release tablets, we use a dissolution curve, and the solid dispersion, we want to predict the physical stability of the formulations. And we use a molecular descriptor to describe the molecules, and we need to split this data into 3 parts: the training set, the validation set, and finally testing set. And the difficulty of the AI, the AI system in formulation development, it is currently for our formulation predicting, it is we just have a very small data set, and with imbalanced the input space. This is the most difficulty. For example, we tracked nearly all the papers. We just get about 100 formulation dataset, and this dataset is very small compared to the other computer AI system. For example, the image recognitions or others. So how to split this kind of data is very important, and also so we try the different method, use a random method, the manual method, and finally we developed our own method. We call it MDFIS algorithms for the dataset splitting, and get a very good performance. And the evaluation criteria, we also develop our own criteria. For example, for the oral disintegration tablet or the FT, we think about if the disintegration time is less than 10 seconds between the prediction time value and the experimental value, we think it is accurate. Otherwise, think it is inaccurate. For this oral sustained release the tablets, we use the similarity factor F2 to predict how it is the prediction value and the experimental value, whether it is similar or not. If this FT value is above 50, we think it is we get the good predictions. For the solid dispersion, we want both the 3 months. We want to see both 3 months the results and the 6 months results, or it is accurate. We think it is good. So this is the results of the prediction. We can see we compared the ANN, that is artificial neural network, and the DNN, the deep neural network. We can see the deep DNN model is much better than the ANN models. And also, for these 3 formulation development, we can see we can get about 70 to 80% accuracy for the DNN models. And so if you want, we developed models, DNN model for the formulation development, and currently also our laboratories developed the other to improve the accuracy of the predictions and develop other algorithms. If you want to know more information, you can check our publications. And our laboratory developed this research computational pharmaceuticals since 2011, when I worked in the Aston University as a lecturer. And in 2014 and in 2015, we published first book in these areas and by the widely publishers. And also we organized several conferences in these areas and did over 50 lectures and invited talks in different conferences. And also the Orton's Pharmaceuticals, the textbook already involved the concept of computational pharmaceuticals.